So, all right, objective 2, we want to graph the cosine function y is equal to cosine of x, and the functions of the form y is equal to a cosine of omega x. So we're doing the same thing as before, but now we're working with cosine. So cosine also has a period of 2 pi. So once again, we really only need to look at the interval 0 to 2 pi. Once again, it's important to look at the important and or easy points to plot. So in the case of cosine, important points would be 0, 1, pi over 2, etc. Easier points, maybe not as important, would be pi over 3, 1/2, 2 pi over 3, -1/2, anything along those lines. So we see our graph of cosine definitely looks different than our graph of sine. Our graph of cosine is going through the y-axis there at 1. It's not going through the origin. So it's going through at its maximum point. And so our full period is then once again at 2 pi when our graph is going to go through the value, the y value of 1 once again. So just like before, this is a graph of one period or cycle of cosine. We also have our table once again. This is found in your book, but we have a table of all of these values written out. So not just in graphical form, but you can see it summarized in a different way. Then we can also go through the properties that cosine has as well. So just like sine, the domain is a set of all real numbers, and the range is all real numbers from -1 to +1, including -1 and +1. So both sine and cosine have the same domain and range. They just vary in what they look like, pretty much. So the cosine function is an even function, so that means that if we plugged in a negative value of x, we would still have that positive cosine value. So it's an even function as the symmetry of the graph is with respect to the y-axis. So now we have symmetry with the y-axis instead of the x-axis. Or instead of reflecting over the x-axis, we now have symmetry over the y-axis. The cosine function is periodic with period of 2 pi, just like sine. And then we see that x-intercepts are going to be at 3 pi over 2, negative pi over 2, pi over 2, 3 pi over 2, 5 pi over 2, and the y-intercept is going to end up being 1. So we see our x-intercepts are going to be those integer multiples of pi over 2. Then we see the maximum value is 1, and it occurs at x equals -2 pi, 0, 2 pi, 4 pi, 6 pi, so even integer multiples of pi. And then the minimum value is -1. That occurs at x equals -pi, pi, 3 pi, 5 pi. So those would occur at odd integer multiples of pi. All right, so fairly similar. We're just looking at, different intercepts, places where minimum and maximum values are different, things like that. But everything else is about the same. They have the same period, they have the same domain, they have the same range. So we'll go ahead and graph we'll graph a cosine function. So we want to graph y is equal to 1/2 cosine 3 of x using transformations and then determine the domain and range. We did not determine the domain and range of our last problem. I just realized that. So when we go ahead and determine our domain and range of this problem, we'll make sure that we go back to our last problem and do that as well. All right, so example 2. We have the same thing as before, where now we have this form of y is equal to a cosine of omega x. So we want to make sure and detail what these mean. So in our function, y is equal to 1/2 cosine of 3x. The 1/2 is going to cause a vertical compression. So before we saw that our value that we're multiplying by sine was a whole number. And so when we multiply by a whole number, we see that's going to end up being stretched, or any value greater than 1. We see that we're stretching that function, but if we have a value less than 1, then that means that we're going to compress our function. So we're going to take the min and max values and we're going to make them smaller. So 1/2 is going to cause a vertical compression by a factor of 2. Our function isn't negative this time, so we don't have to worry about reflecting anything. When we say cause vertical compression by a factor of 2, this means we're dividing our y values by 2, pretty much. We're cutting them in half. All right, and then our 3 is also going to cause a horizontal compression. So we're taking our original graph of cosine, and for our problem, what we're going to do is that we are going to vertically compress. So we'd say vertically compress, and we are going to horizontally compress. So we're going to take this original graph, we're going to compress it vertically, so we're going to bring those min and max values closer together, and then we're going to scoop the curves together, essentially. We're going to compress them inwards. So what this means for our actual values, this means that our min and max values, I have more room down here, so we'll write our room down here instead. All right. So our min and max values will now be (1/2) and (-1/2). So these are now going to be our minimum and maximum values. So our minimum and our maximum values will still be occurring in the same pattern, but remember now we're also compressing by a factor of 3. So this means that where we had those important points, so where our graph either crossed the x-axis or had a minimum and maximum value, those values are going to be divided out by 3. We're compressing by 3, so each one of these important points is going to need to be divided by 3 in order to get our new graph. So this means that we'll see our graph will cross the x-axis now, or have x-intercepts at these values divided by 3. So we're going to see it cross our x-axis at, we have positive values, so we're going to see it cross at pi over 6 and pi over 2 and 5 pi over 6 and so on. So originally our graph crosses the x-axis at pi over 2 and 3 pi over 2. So we're dividing those by 3 to give us pi over 6, pi over 2, and so on. Then our minimum values will be at, we'll look at our minimum values. So our minimum values here, we're dividing these by 3 as well. So these will occur at negative, sorry, we're not doing negative, so pi over 3, pi over 3, pi itself, and so on. Then our maximum values, lastly here before we go ahead and graph, our maximum values occurred at 0, 2 pi, 4 pi, 6 pi. So this is going to be 0, 2 pi over 3, 4 pi over 3. All right, so we've gone over kind of what these transformations are going to do to our graphs. Now we can go ahead and actually start graphing. So we know that we have a maximum value at 0, and these maximum values are going to be 1/2. Let's go ahead and mark our graph up before we go ahead and do this. So our maximum value is going to be 1/2. Our minimum value is going to be negative 1/2. So let's say that these points in between are going to be 1/4 and negative 1/4. Then on our x-axis here, we are going to start with pi over 6. Then we'll have pi over 3. Then we'll have pi over 2. Then 2 pi over 3. 5 pi over 6. This is going to be pi. Then we have 7 pi over 6. And lastly, 3 pi over 4. And now we can plot our points. So we have a maximum value at 0. So we'll have a point up here. Our graph is going to be crossing the x-axis with pi over 6. We will have a minimum value at pi over 3. Our graph will cross again at pi over 2. And we have another maximum value at 2 pi over 3. So let's go ahead and connect these points. We see that if we connect them, they'll look something like this. And for cosine, this is 1 period. So we saw that our period of cosine regularly was going to be 2 pi, but since we compressed by a factor of 3, that means we divided 2 pi by 3 to get 2 pi over 3. So 1 period will then be 2 pi over 3 for this new graph. So now we can just continue on. We know what our graph is going to look like now, and we can continue on with our points. So our graph is going to cross the x-axis again at 5 pi over 6. It's going to have a minimum value at pi. It's going to cross our x-axis again at 7 pi over 6 and have a maximum value at 3 pi over 4. So this is just following along with the pattern that we already established with our first period there. So this is what our graph would end up looking like here. And if you wanted, you could always draw in the points that they actually are. So this would be pi over 6, 0. This is 0, 1/2. This is pi over 3, negative 1/2. Pi over 2, 0. 2 pi over 3, 1/2. 5 pi over 6, 0. This is pi, negative 1/2, and so on. So you can mark these points if you'd like as well, just to clarify what they are. And the last part of this question, determine the domain and range, which we'll then go ahead and do for that first example as well. If we wanted to determine the domain, we know that the domain for cosine is going to be all real numbers. And by looking at this graph, we know, or we kind of see that our graph is going to continue on in either direction. So this means that our domain is also going to be all real numbers. So our domain stays the same. All real numbers. And our range was compressed. So it was originally between -1 and 1. Now our range we saw was compressed by 2, which means that it's now -1 to 1, -1/2 to +1/2. So then our range in interval notation is -1/2 to +1/2. So that would be for our problem using cosine. So let's go ahead and determine that domain and range for example 1, and then we'll go ahead and move on. So in our example for number 1, for the domain, it's the same thing. We see that the domain is still going to be all real numbers since our function will continue on in either direction. So our domain stays the same. All real numbers. And our range was stretched. So our range before, just like in cosine, it was -1 and +1, but we multiplied by 3 or -3 in this case. The negative doesn't affect our range since we see that our maximum value is still going to be at 3 and our minimum value is still going to be at -3. So our range in interval notation is now going to be -3 to +3. So that would be the domain and range for our sine function. So all right, let's go ahead and move on to our next objective here. So objective 3, we wanted to determine the amplitude and period of the sinusoidal functions. So the sine and cosine functions are referred to as the sinusoidal functions. So both sine and cosine are considered our sinusoidal functions. This is because if we shift the graph of y is equal to cosine of x to the right, pi over 2 units to get y is equal to cosine of x minus pi over 2, this is the same graph as y is equal to sine of x. So looking at our first picture here, we have y is equal to cosine of x as our purple graph and y is equal to cosine of x minus pi over 2 as our blue graph. So we see that minus pi over 2, it just took our graph and it just shifted it pi over 2 units to the right here. Then we can look at our next graph in the next picture over, which is y is equal to sine of x, and we can recognize that y is equal to sine of x is the same as y is equal to cosine of x minus pi over 2. So that shift that we made to our graph of cosine essentially gave us the same graph as sine. So from this, we can determine that sine of x is just equal to cosine of x minus pi over 2. So that's why we consider them sinusoidal functions. They have the same pattern to them, they're just shifted. So then the graphs of functions y is equal to a sine of omega x and y is equal to a cosine omega x, these are referred to as sinusoidal graphs. The values of the function y is equal to a sine of x and y is equal to a cosine of x, where a does not equal 0, satisfy the inequalities where we have negative absolute value of a is less than or equal to a times sine of x, which is less than the absolute value of a. Also similarly with cosine, we have the negative absolute value of a is less than or equal to a times cosine of x, which is less than or equal to the absolute value of a. This just being said that the absolute value of A is the amplitude of our graphs of y is equal to A sine of x or y is equal to A cosine of x. So the value that we're multiplying in front of sine or cosine, that value is going to be our amplitude. It just changes our range essentially. So we see here in our image, we have y is equal to A sine of x, where A is greater than 0. Our period is still 2 pi, but now we see that this range is from negative A to A. So we see that that's how our amplitude affects these functions. Then we can go ahead and assume that omega is greater than 0. Will never be less than 0. We always assume omega is greater than 0. And we can get the theorem for the period as well. So if omega is greater than 0, the amplitude and period of y is equal to A sine of omega x and y is equal to A cosine of omega x are given then by amplitude is equal to the absolute value of A, and the period is equal to t, which we recognize as 2 pi divided by omega. So now just by looking at the equation, we can very quickly determine the amplitude and period of our equation just using these definitions. So for example 3, we're going to go ahead and find the amplitude and period of each function. So for A, we have y is equal to negative 1/2 sine of 4x. So if we want to find our amplitude, we'll write amp. So our amplitude, which is the absolute value of A, our A value in this case is 1/2, or negative 1/2. So we're taking the absolute value of negative 1/2, which then gives us positive 1/2. So our amplitude is 1/2. Then our period, which I'll write PER, is equal to, and we can signify period as T. So T is equal to 2 pi divided by omega, where in this case we see 4 is omega. So then we get 2 pi over 4, which just gives us pi over 2. So for the case of this problem, just by using the definitions and picking the values out of our equation, we got that their amplitude is 1/2 and our period is going to be pi over 2. So now doing the same thing for part B, we want to find our amplitude or our amp. 3 is going to be our A and 1/3 is going to be our omega. So our amplitude, which we said was the absolute value of A, is going to be the absolute value of 3, which is then just 3. And the period, which we recognize as T, will be 2 pi over omega, where omega is 1/3. So this ends up being 2 pi divided by 1/3, or 2 pi times 3. So our period in this case will end up being 6 pi. So instead of vertically compressing our graph, we're now horizontally stretching our graph. So now we're able to pick out our amplitude and period very quickly, which then help us with actually graphing.